Is the universe in a black hole, and does that answer all our big cosmic questions about the Big Bang and what's next to the universe? Could well be, and in this video we go together on a wild journey through space and time, so buckle up well and get ready for a cosmic identity crisis. And if you like it, you can help me a lot with a thumbs up and a comment, because this will activate the YouTube algorithm to display this exciting topic to even more people. Thanks guys, and welcome. What was before the Big Bang? What is next to the universe, and why can't we get out of the universe? Amazingly good answers to all these questions are given by the theory that the whole cosmos is in a black hole. We make a small statistical survey from it. Write me now at the beginning of the video times how you stand to this theory. Could the universe be, in your opinion, really in a black hole or not? And at the end of the video, we'll take another look at whether the mood has changed. To understand if the whole cosmos is hosted by a black hole, we should first look at what a black hole is in the first place, because these things are really the most fascinating objects of the cosmos for me. There are many misconceptions about gravity monsters, such as that they suck up everything. If that were the case, however, our Earth would have been swallowed long ago. Let's start with a little history lesson. Already in the year 1783, the idea of a black hole was described for the first time by the English natural scientist John Michell, who described the whole thing still as a dark star. Sounds a bit like the Death Star, but was actually already a very accurate description of black holes. He formulated it as follows. If the radius of a sphere of the same density as the Sun exceeded that of the Sun in a ratio of 500 to 1, a body falling towards it from an infinite height would have a higher velocity at its surface than that attained by light. Consequently, assuming that light is attracted by the same force in proportion to its mass as other bodies, all light emitted by such a body would return to it due to its own gravity. This is true under the assumption that light is affected by gravity in the same way as massive objects. At the beginning of the 20th century, Albert Einstein with his theory of relativity and Carl Schwarzschild with his calculations lived the physical basis for the description of black holes. Schwarzschild coined the terms event horizon and singularity and calculated that every object in a certain area cannot let the light escape if it is only sufficiently compressed. If, for example, the mass of the Sun would be compressed to a radius of just 3 kilometers, no ray of light could escape from its surface, so each of us could become a black hole if only we are compressed enough. Now that's a great prospect. For a long time, black holes were only physical theory. Definitive evidence could be gathered only when technology became more advanced. Today there are no more doubts about the existence of black holes. At the latest, since one could calculate in 2019 from radio images of the so-called Event Horizon Telescope the representation of the supermassive black hole of the galaxy M87. Quite photogenic, I would say. But what exactly is a black hole? Let's try a definition in one sentence. A black hole is an object whose mass is so compressed that in a certain area even the light can't escape the gravity. So the decisive aspect is the event horizon. The event horizon is the border, behind which the gravity is so strong that not even the light can escape anymore. According to Albert Einstein's theory of relativity, the speed of light is the fastest thing that can exist within the universe. So if not even the light can escape, then nothing can escape at all. Nothing can cross an event horizon from the inside to the outside. No information, no radiation, and certainly no matter. This already disproves a persistent prejudice about black holes, namely that they would suck in everything. Much more their mass determines their gravitational influence. The heavier a black hole, the farther the event horizon bulges outward, but no black hole sucks in everything, no matter how far away it is. For example, it would also be conceivable to turn tiny little objects into a black hole. For example, this gummy bear. I would only have to compress it enough. Then it would form a tiny event horizon, but this gravity would not even be enough to suck me in. The other way around. And even if gravity has its effect, it does not mean that one is sucked into the center towards the singularity. In the center of our galaxy, the Milky Way, for example, there is a black hole called Sagittarius, a star. This monster grasps our solar system quite with its gravity. Just at this moment we rotate around the center of our galaxy. For one rotation, we need about 225 million years. A so-called galactic year. However, we are not moving closer to Sagittarius, a star. Our rotation orbit is stable. As with the Earth and the Sun grasps the Earth, but the Earth is not sucked into the Sun. Oops! So black holes differ by their mass. This prompted physicist John Archibald Wheeler to make his famous statement, "Black holes have no hair." He meant that they have no properties except their mass and at most their angular momentum and their electric charge. This results in different types of black holes: supermassive black holes, stellar black holes, and primordial black holes. Supermassive black holes form the core of galaxies and are incredibly heavy. They weigh at least several million times as much as the Sun. One of the heaviest examples, Ton 618, even weighs 66 billion solar masses. Researchers disagree on whether the supermassive black holes were there first and then stars gathered around them and ultimately formed galaxies, or whether the galaxies were there first and a black hole formed from their condensed mass at the center. A bit, so the question of the hen and the egg, or rather black hole and galaxy. Then there are the stellar black holes. These represent the end product of really heavy stars. Stars do not exist forever. The average star can run its fusion process for about 10 billion years, generating heat and energy. When it has no more elements to fuse, that's it. Most stars then expand into a red giant and become many times larger than in their original form. Heavy stars explosively eject their gas shells into space, and this is called a supernova. In the case of very, very heavy stars, part of their mass can collapse and become so compressed that an event horizon is formed, i.e. a black hole. Researchers assume that there are at least 10 million stellar black holes in our Milky Way alone. That is, everywhere where a sufficiently massive star has collapsed. And then there are, maybe, the mysterious primordial black holes. We have already learned that theoretically also very light objects could be compressed to a black hole. But under the conditions prevailing in the universe now, this hardly seems possible. With what force, for instance, should a light object like, oh, another gummy bear, be compressed to the point of creating an event horizon? Shortly after the Big Bang, i.e. the beginning of the universe, the conditions were so extreme that it seems conceivable that a lot of mini black holes, or primordial black holes with the expert term, were formed at that time. At that time, there were no stars that could have collapsed, but there were highly compressed regions in the primordial soup of the universe that may have been squeezed together to form tiny black holes. Such a primordial black hole would not even have the gravity to swallow the Earth, for example. If it came too close to us, it would simply hurtle through the Earth, causing at most a few earthquakes. One question immediately comes to the mind of many when they think of black holes. Where would you actually end up if you were swallowed up by a black hole? Unfortunately, one must call their weather scenarios from many Hollywood films somewhat unrealistic. If you got too close in the black hole, you would first be whirled around in a so-called accretion disk together with all the other stuff that was caught by gravity, i.e. gas, dust, and so on. Within this accretion disk, immense temperatures can develop by friction, so that one was probably properly roasted. Eventually, one would cross the event horizon at some point, but one would not even notice it. We can't perceive any information from inside the event horizon from the outside, but from the inside everything seems quite normal. So as normal as the things just appear if one is sucked straight into a black hole. Meanwhile, you will be spaghettified. Spaghettization is a scientific term that can be used generously in any doctoral thesis, and was coined by the British scientist Stephen Hawking. He meant with it that objects on the way to the center of the black hole are stretched by the gravity and the rotation in the length. So you literally become a very, very, very long space spaghetti. Okay, last food pun, I promise. And then, very likely, you will come out nowhere and not somewhere else. You become part of the black hole itself, a so-called singularity. An inconceivably condensed point, without expansion, not even a millimeter in size. Your mass becomes part of it and the black hole becomes heavier, causing the event horizon to move minimally further out. A few scientists consider it possible that also white holes exist. These would be then the exact counterpart to a black hole. While one cannot pass the event horizon of a black hole from the inside to the outside, one cannot pass the event horizon of a white hole from the outside to the inside. In other words, it spits out everything. If you think about it further, every black hole could be connected to a white hole. You go into the black hole and comes out of a white hole. This connection would then be a kind of wormhole, but this is only absolute theory. One last thing, do black holes exist forever, devouring more and more and getting bigger and bigger? Almost. Stephen Hawking goes down not only as inventor of the term spaghettification into the history books, but also as discoverer of the so far not yet doubt-proved Hawking radiation. Hawking assumed that, so to speak, exactly from the event horizon particles were created by mysterious quantum effects which then can leave the black hole. In this way, black holes would lose their mass, but very slowly. So slowly, that probably black holes will be the very last objects, which will exist shortly before the universe dies. But that is again a completely different topic. I hope the subject of black holes has captivated you. I will deal only a little more exactly with the topic spaghettification and gummy bears. Now we know, so what black holes are basically, but so that our entire universe could fit in there, would really need a massive specimen. But what do we know about what happens inside a black hole? NASA tried to listen very closely and actually received sounds from a black hole. And the somewhat creepy original recordings, you can hear them now. In space, I can't hear anyone screaming because there is no sound. Right? It's not quite true. It is a widespread misconception, and because it is not true, researchers have now been able to make even a black hole audible. Black holes are objects whose mass is so compressed in a certain area that a singularity is created, a point which is so squeezed together that it has no more extension, not even a millimeter. Around this singularity the gravity is very strong, and in a certain radius even the light cannot escape. The border, behind which the light cannot resist the gravity anymore, is called event horizon, and depending on how heavy the black hole is, this event horizon reaches just bigger and bigger dimensions. Everything could theoretically become a black hole, it would only have to be sufficiently compressed. If you would manage to squeeze together enough and to become a singularity, you would also have a mini event horizon and become a black hole. Please don't try this at home. Despite their engaging nature, black holes also affect their surroundings. They emit violent beams of energy called jets. These are created when matter accumulates around a black hole in an accretion disk. Huge amounts of energy are created in the accretion disk, which are eventually discharged into the cosmos as jets. Black holes emit, but also gravitational and pressure waves. So, all in all, it can be said that black holes not only swallow lots of stuff, but also emit effects that affect their surroundings, and NASA researchers have taken advantage of this. They observed a black hole in the Perseus galaxy cluster, at a distance of a mere 240 million light-years. NASA wrote in a news release, astronomers discovered that the pressure waves emitted by the black hole cause ripples in the cluster's hot gas. That can be translated into a sound, one that humans can't hear, about 57 octaves below middle C. So the black hole interacts with the surrounding hot gas nebulae, and NASA was able to convert that into audible frequencies. And I don't want to keep you in suspense any longer. Hold on tight. This is what a black hole sounds like. Okay, that had to be. But now, this is what a black hole sounds like. Creepy, or on the other hand, not worse than most of what's in the charts at the moment. I find it especially somehow spacey, I don't know how else to describe it. But it could work as a background sound of Star Trek, couldn't it? Feel free to write me in the comments what your feelings were when listening to Black Hole and how you would describe the sound. I'd be very interested, and I'll try to answer as many comments as possible, I promise. By the way, the sound is not exactly what you would hear if you were near the black hole, because humans would not be able to hear the original sound. And if you were near a black hole, you would have very different problems. The NASA researchers have translated the sound into the audible range for us humans. The signals in this form, as we have just heard them, are up to 288 quadrillion times higher than their original frequency. Such a procedure is called sonification. But why can we hear something in space now? As I said at the beginning, it is a misconception that there are no sounds in space. The largest part of space is of course a vacuum, in which no sound waves can propagate. In this large part the prejudice is true that you can actually hear nothing there. and no one hears you scream when the aliens attack you. But the vacuum is not perfect everywhere. In places like galaxy clusters, there are large amounts of intergalactic gas that envelop hundreds or even thousands of galaxies. Like some kind of gas soup that galaxies float in. Super thin and impossible to see with the naked eye, but this intergalactic gas is sufficient as a medium for propagating sound waves. Here a beautiful paraphrase of a NASA researcher. It's like a beautiful film score by Hans Zimmer with a very high mood level. The idea that there are these supermassive black holes scattered throughout the universe emitting incredible songs is a very tantalizing thought. I wonder when the first black hole remix will be uploaded to YouTube by anyone. If you are talented DJs, then create a remix of it and let me know. Runs with me the whole day on continuous loop, the black hole sound. Imagine our universe would really be in a black hole and aliens, who examine it from the outside, hear then all the time so muffled island boys whining from the black hole.
I'm an island bird, and I'm trying to make it. I'm an island.
But now we still don't know for sure if we live in the black hole. Maybe we will find out more when we study the oldest black holes in the universe, the ones that were formed shortly after the beginning of time, the Big Bang. The James Webb Telescope is so powerful that it can target these things. Check it out. James Webb has observed a cluster of galaxies more than 11 billion light-years away revolving around a red quasar and being virtually eaten. Quite dramatic. But from the beginning, an international team of scientists has pointed the James Webb Space Telescope at a very special object, namely, a rare red and extremely bright quasar poetically named SDSSJ-165202.64+. 172852.3. Oh. Now the time for the video is already over, unfortunately. Bye guys. There is a little bit more to tell, of course. First, let's clarify what a quasar actually is. It's not some weird magical creature from the Hogwarts world or something, but quasar stands for quasi-stellar radio source. So it's an extremely distant source of radio radiation, and commonly researchers use it to refer to the active nucleus in a galaxy. If you observe this nucleus through a high-quality telescope, this bright spot looks star-shaped. And that's where the term quasar came from. A quasar emits an incredible amount of energy in different wavelengths, and today we know that these things really have nothing to do with stars, but that a quasar is a black hole in the center of a galaxy, with a rotating accretion disk full of luminous and energetic matter. This luminous matter races around the black hole, around the galactic core. From our point of view, the matter first races away from us and thus experiences a red shift, and at the same time the matter then grasses back towards us on the other side of the nucleus, and thus there is a blue shift. Because the spectral lines in the spectrum are so broadened, researchers can therefore distinguish quasars very well from stars that do not have these enormous shifts. What we can see from quasars is the enormous accretion disk of material that radiates super amounts of energy into space. These objects are among the most luminous and energetic objects in all of space. For this winter it would be really handy to have a quasar in the gas boiler. The oldest and most distant quasar is 13.11 billion light-years from Earth, and the black hole has an incredible mass of 1.6 billion sun-day. The brightest quasar discovered so far shines about as bright, and now brace yourselves, as 600 trillion suns. Unimaginable. Okay, now we have some idea of what a quasar is. And the quasar we're talking about here is unusually red to begin with, and that's because of this red shift of the luminous material in the accretion disk that I just mentioned. And around this quasar galaxies have accumulated. This is nothing new, because Hubble had already taken a look at this quasar, and the researchers concluded from the data that the host galaxy of the quasar has joined forces with another galaxy. So far, so normal and unspectacular, if one can say so. At the time, however, it was not expected that there would actually be several galaxies racing around the quasar. Astronomer Dominika Wilczalek from the University of Heidelberg says, there are few known galaxy protoclusters at this early date. They are very hard to find, and very few have had time to form since the Big Bang. So it means that James Webb managed to observe an ancient galaxy cluster in the early universe. By the way, galaxy cluster is nothing else than a cluster of galaxies. Our Milky Way, for example, is located in the so-called local group. This is not a mediocre village pub band or something, but really a cluster of galaxies with a size of incredible 5 to 8 million light-years. Besides the Milky Way, the local group also includes the Andromeda Galaxy and more than 70 dwarf galaxies. And so with the help of James Webb and the near-infrared spectrograph, NIRSpec for short, they've now found that a whole 3 galaxies are spinning around the quasar and swirling around each other. And they're doing it at an insane speed. Imagine what an enormous mass collection this gigantic black hole must be. By the way, the special thing about the NIRSpec instrument is that you can collect spectra over the entire field of view of the telescope at the same time, not just from a single point. So James Webb could scan the quasar, the 3 galaxies and the surrounding area in the same way. Nadia Zakamska, a physicist at Johns Hopkins University, thought to herself about the data. After we got the James Webb data, I thought, I have no idea what we're even looking at here. What is all this stuff? We spent several weeks staring at these images. I know that feeling. I always have that feeling when I have to clean up my room and stare at the mess. However, based on the spectra provided, the researchers were finally able to figure out that the red quasar was indeed part of this dense galaxy node. So this quasar could simply be the super-hyperactive core of an entire galaxy cluster. The team now believes that this whole structure could be one of the densest known areas of galaxy formation in the earlier universe. Even a dense dark matter knot is not enough to explain this. We think we might see a region where 2 massive dark matter halos merge, says Weil Zalek in response. A dark matter halo, by the way, is the corona that surrounds galaxies, a kind of cover from dark matter which holds together the galaxy. However, this is everything only totally hypothetical, because still nobody knows so properly what dark matter should be at all. So, I don't know about you, but I am speechless every time James Webb has discovered something new again. It's just incredible how far back into space this telescope can look, back into the past. Photos of clusters of galaxies formed from billions of years ago in the earliest universe, gathering around a giant, man-eating black hole, that's now available with this data. That is really crazy. Of course, the researchers will now collect even more data, and all these findings should help us in the future to understand how galaxy clusters in the early universe came into being in the first place, and then ultimately formed the cosmic web that we know today. There are still so many mysteries in the universe, you can't really decide what the James Webb telescope should look at next. Let me know in the comments what you would like James Webb to study. Objects in our solar system, exoplanets with potential alien life, or the region just after the Big Bang. I'm super excited to hear your suggestions and I'll try to answer as much as I can, too. Promise. Now we have already learned a lot about black holes. Let's take all this information together and finally clarify whether the universe could really be surrounded by the event horizon of a black hole, whether there is a mother universe outside this cosmos, and whether there might be another daughter universe inside every black hole in our universe. Well, fasten your seatbelts, people, now it becomes crazy. Let's start with an idea from none other than Stephen Hawking. Hawking thought it possible that every time a black hole is created in our universe, a baby universe could be created, accessible only to an observer who is within the event horizon of the black hole. What a fascinating thought! Imagine being caught in the gravitational pull of a black hole, crossing the event horizon, and perhaps a whole new, exciting universe awaits you instead of death. Just don't try this, folks. I don't want to be responsible for spaghettification deaths. If one spins this idea of Stephen Hawking further, then the thought is obvious that also our universe could be in a black hole. The astrophysicist Ethan Siegel has worked intensively on this, and has collected many indications that make this theory seem absolutely plausible. He writes, could our universe actually have been spawned by a black hole that originated in some kind of great mother universe? And do we give birth to a new universe every time a black hole is created? It's a fascinating idea worth exploring. Maybe first, very briefly, the basics, why one has come on this idea at all. A black hole is an object which is compressed and has so much gravity that in a certain area even the light cannot escape. The boundary of this light-swallowing area is called the event horizon, and the heavier the black hole, the farther the event horizon shifts outward. And what happens behind this event horizon, we don't know, because if even light doesn't get out there anymore, then absolutely no information gets out at all. So this offers a lot of room for speculation. Our universe is a multidimensional space which expands permanently. It expands with superluminal speed, so that we can probably not reach the end of the cosmos. But contrary to popular belief, there is an end somewhere, even if it probably won't simply be a wall like in the movie The Truman Show. Or maybe there is. Honestly, nothing would really surprise me anymore. What would be now, if the border of our universe would be the event horizon of a black hole which is in an even bigger mother universe? You still don't believe me, do you? Extraordinary assertions require extraordinary proofs, Carl Sagan already said, and therefore here now some circumstantial evidence comes, which will change your opinion. There are estimates about the total weight of the universe. If one counts the mass and energy of all particles contained in the visible universe together, one can ask the question, how big would be the event horizon of a black hole with this mass? And the result is, the event horizon of a black hole with the mass of our universe would be approximately as large as the dimensions of the observable universe. What is the probability that this is a coincidence? Maybe some of you are still resisting and saying,
the universe is way too big, it can't be squeezed into a black hole, can it?
Let's break this down. What would it mean if our universe was in the center of a black hole? That would indeed mean that the universe would be completely squeezed together, to put it scientifically. Because the black hole itself is an inconceivably compressed and small point, a singularity and accumulation of mass without expansion. The more the black hole swallows, the heavier the singularity becomes. But not bigger. Because the special peculiarity of a singularity is just that it always remains inconceivably small, and possesses such a tiny extension that one could not describe it with any size specification. And this concept of the singularity prepares the physicists already for a long time head to rack, because an inconceivably condensed point without extension stands so a little on war foot with the laws of the physics. Even Albert Einstein has often tried to somehow get around the result that black holes and singularities could exist, although just as discovered Einstein's laws predict the existence of black holes and thus also singularities. It is so unbelievable that even Einstein himself did not want to admit it. Long story short, since we have no idea what bizarre laws govern the nature of the singularity, it could be absolutely possible that we are inside such a singularity and don't know it. The matching size of the event horizon of a potential black hole and that of the observable universe is a strong indication. Another indication could be the expansion of the cosmos. Since origin of the universe, according to widespread opinion in the so-called Big Bang, about 13.8 billion years ago, the universe grows. It has begun according to the Big Bang theory in a singularity, like a black hole. But mysteriously the expansion does not weaken. The longer the Big Bang is ago, what would be expected? But it increases more and more. Why this is so is absolutely inexplicable, and physicists have therefore developed the concept of dark energy. Dark energy apparently makes the cosmos grow faster, but no one knows what dark energy is. How about this? Dark energy is an interaction of our cosmos with the area outside the black hole, an interaction with the mother universe. Perhaps the black hole we are in has been in the growth phase since the beginning of cosmology because it is swallowing more matter. This makes it heavier, and the event horizon, that is, the boundary of the observable universe, shifts outward. I know, it sounds almost too comprehensible to be true.
Sometimes everything is just very simple.
And a third argument, the absence of white holes, sounds like a sequel to The Silence of the Lambs, but simply means the fact that we have never discovered a white hole in the wild anywhere in the cosmos. White holes are the theoretical opposite of black holes. You cannot cross the event horizon of a black hole from the inside to the outside. One is trapped in the black hole. You can't cross the event horizon of a white hole from the outside in, so you can't get in. So you could say that black holes swallow matter, white holes spit it back out. And the connection between a black hole and a white hole could be an Einstein-Rose bridge, better known by the term wormhole. Now for the mysterious, white holes are conceivable according to Albert Einstein's theory of relativity, and so far everything has actually been discovered at some point that is conceivable according to Einstein's theories. White holes, however, not yet. Maybe for the following reason: our universe is connected with the mother universe by an Einstein-Rosen bridge, and that's why we have never found a white hole, because the view into the mother universe, beyond our event horizon, is not possible for us. Just as well it could be that every black hole in our universe would spit you out into a daughter universe from a white hole. Black holes as an entrance into a wormhole whose exit is a white hole into another universe. Other people have to consume lots of things to come up with such ideas. Now these were some arguments for the hypothesis, but of course one must also note that they are not proofs. Ethan Ziegel writes, "What is sadly missing is the crucial step of a clearly identifiable signature. We don't know if our universe was created by the formation of a black hole, but at this point it's a tantalizing possibility that we shouldn't rule out." I find the indications relatively strong, but I also think that the black hole hypothesis has a big disadvantage. It shifts the question about the origin of our cosmos again only on another level. We would know then that our universe has originated within a black hole. But how did the mother universe originate? Also in such a way? But what was then the beginning of everything? And already we stand again before the biggest question of all and have not really got further. But the science would not be the science if there were not also counter-opinions. And now another group of astronomers comes and says, no, the universe is not in a black hole. The universe is in a white hole. And if you already found that with the black hole unbelievable, then look at this. How did the universe actually come into being? Where does all this come from, and how could it come to the exceedingly strange circumstance that we can stand here now and think about the mysterious cosmos? Short review of what happened so far. Our universe exists according to the opinion of most astrophysicists since 13.8 billion years. The starting point, according to the prevailing opinion, was the Big Bang, an act of the self-creation of the cosmos. All the energy and matter that flies through space today in the form of planets, nebulae, stars, charming YouTubers, and so on was squeezed into a tiny point, one of the singularity. Then, for ominous reasons, that dot began to grow. And grow. Until today. And today, of course, space has reached gigantic proportions and is filled with billions, if I may say trillions, of galaxies, and it is still expanding. The vast majority of galaxies are moving away from us as we speak. That is the cosmological state of the things very roughly summarized. Now one could ask a very justified question: why? Most astrophysicists say, simply so. The universe has originated from the nothing, and before the universe was therefore simply nothing. But there is also the exciting theory that our universe is the product of a white hole. But for this we must clarify first what a white hole is at all. You can imagine the whole thing a little bit like the counterpart to a black hole. Very simplified spoken, black holes attract things, white holes spit things out. While behind the event horizon of a black hole no force of physics can escape, not even the light, the event horizon of a white hole could not overcome any force of physics from outside, so you would not get in at all. That would be probably as if you would try all the time to get onto a bouncy castle, but would be pushed out again at every attempt. And if one spins this idea further, every black hole could be connected with a white hole. This connection of these space-time tunnels would then be an Einstein-Rose bridge, or colloquially a wormhole. Who can be sucked negligently into a black hole could be spat out completely somewhere else in the universe from a white hole. But this is only theory, because the practical proof for the existence of white holes is still missing. No white hole has yet been found in the wild, but they are possible within the framework of Albert Einstein's famous field equation. By its solution one could predict the existence of black holes theoretically, long before one could make the first picture of a black hole. Up to now Albert Einstein was actually still right with everything, and therefore one could argue that also white holes exist, but we have not discovered them simply because of insufficient technical means yet. And another argument for the existence of white holes is the so-called information paradox. If something disappears behind the event horizon of a black hole and then ultimately becomes part of the singularity, the information of the swallowed something is lost. This is because the interior of a black hole no longer has any information except for its mass, electric charge, and angular momentum. One cannot collect more data about a black hole. The famous physicist John Wheeler described it a little bit strangely with the sentence, "Black holes have no hair," so quasi-nothing on the basis of which one could describe them. Very strangely formulated, however, there is a quantum physical principle which says that information cannot be lost, the postulate of the unitarity of the time evolution. What? Put more simply, according to quantum physics, information cannot be irretrievably lost. But in a black hole, this is exactly what seems to happen. Paradox. The solution for this information paradox could be, correctly, white holes. The information might not be lost at all. Hidden from our prying eyes, it is simply burped out of a white hole somewhere else. This burp served only the science. The principle of the black-white hole relationship not also perfectly transferred to the entire universe? The physicist Hal Haggard thinks this is very possible and says, why not investigate whether white holes have such interesting consequences? The geometry is very similar in both cases. It even goes so far that they are sometimes mathematically identical. The connecting point is the singularity. In the center of black holes, as well as of white holes, there is a singularity. And also our universe began in a singularity. Could our universe be born therefore from a white hole, whose singularity was a universe seed so to speak, from which everything blossoms now for billions of years like a tender little plant? In order to understand this still better, we must move a little bit in the area of the quantum physics, thus the ominous part of the physics which deals with the very smallest elementary particles. For singularities, the principles of classical physics fail a bit, because an infinitely small, infinitely condensed point is not really possible or describable. Some quantum theorists therefore quantize spacetime and postulate a quantum theory of gravity. They conclude that the classical physics view of black holes and co. is incomplete. According to the theory of loop quantum gravity, the basic building blocks of spacetime have the form of extremely small loops, quantum loops. And these loops have a finite, thus describable size, thus would be in agreement with the physics. Let's imagine a very, very heavy star that is about to collapse. That is, it ends up in a hypernova and compresses its remaining mass in such a way that a black hole is formed. According to quantum loop theory, this squeezing of the star cannot reach the point of singularity, that is, the point of infinite density. Instead, before reaching the point singularity, the star would experience a quantum jump. At a certain pressure, pressing on the residual mass of the star, the black hole turns into a white hole. This process of transformation of a black hole into a white hole would take only fractions of a second, and exactly this loop quantum jump of a dying star could be the starting point of a new universe. Our universe could have originated, in which somewhere else in a mother universe a very heavy object collapsed and created a white hole by a quantum jump. By a cosmic burp, to use this technical term once further. Finally the whole mass and energy was hurled over the event horizon of the white hole and our universe saw the light of the world. Physicist Lee Smolins popularized this theory and he describes it like this. A star that collapses to a black hole is compressed very quickly to an infinite density and time stops. Instead of collapsing to an infinite density, the star collapses to a certain extreme density, then bounces back and begins to expand again. The point where time ends inside a black hole is connected to the point where time begins in a Big Bang in a new universe. Phew, that was really a wild ride through space and time. As announced at the beginning, let's see how the mood is now. Did you change your opinion concerning the theory of the cosmos in the black hole in the course of the video? Did you consider it improbable at the beginning and now possible, or vice versa? Write it to me very gladly in the comments. I look forward to the exciting cosmic discussions with you. Speaking of unimaginable dimension, my channel is very close to 5,000 subscribers, and I know from the YouTube statistics that the majority of all viewers have not subscribed at all. This is absolutely free, helps me immensely, and you no longer miss galactic videos. So people, like all times, press the subscription button, and in the next video it will be exciting again. We will find out what Milankovitch cycles are all about and how they will shake up our climate. So don't miss it and tune in again next Tuesday. Otherwise, I'd say see you in the next video. Take care, guys.